Hi, everyone. Thanks for coming back. We're doing Ken Schiller's number 22 today, and we have a pretty special paper. I was just actually going through it. It's pretty interesting. And thank you, Lacey, for reading again with us today.
Yeah, thank you for letting me read this.
Hmm.
Charge Clusters in Action by Ken Shoulders and Steve Shoulders, Bodega, California. New energy transformations have been found using highly organized micron-sized clusters of electrons or EVs having soliton behavior, with the electron populations on the order of Avogadro's number. When interacted with solid material, these charge clusters perform a low energy phase transformation type of atomic disruption that liquefies the lattice and propels the material to a high velocity without apparent signs of conventional heating. Using an ordinary thermal interpretation, a thermal gradient for bulk material greater than 26,000 degrees Celsius per micrometer would be required to achieve these effects. Evidence will be shown for the EV transiting the solid material, fluidizing it by contributing one extra electron per nucleon for a period considerably longer than the relaxation time, and then imparting momentum to the fluid. Under such conditions, the impact of this fluid on another solid buries a slug of solidified material to a depth of over 20 micrometers. This abnormal behavior introduces the notion of energy gain produced through a low energy atomic and molecular phase change, coupled with high recombination energy release. Evidence will also be introduced for the underlying energy production process stemming from the equivalence of an electron annihilation energy release based on the manipulation of fractional electronic charge. Scanning electron micrographs will be introduced showing EV borehole perfection, dual EV existence, and an electrically driven sloshing type of material reflection in the borehole that is correctable with impedance matching micronozzles. Microthrusters using a 20 micrometer diameter and 100 micrometer long slug of non-explosive material will be discussed that are based on a spark-like propulsion process, giving sufficient velocity to produce shock cones 70 micrometers apart at atmospheric pressure after being initiated from an energy source of 20 microjoules. In vacuum, the ions form such a source travel 1 centimeter in 50 nanoseconds. As an example of the new energetics produced by EV interaction with material, data will be submitted on an intense light source having dimensions of a few micrometers and duration of several picoseconds arising from a form of synchrotron radiation. The basis for controlling the wavelength of this photon source from the visible light region to gamma wavelengths will be discussed. Micrographs will be shown of a low energy nuclear reaction that has produced nuclear transmutations by using a nuclear charge reaction process. Background. This paper is about several interrelated discoveries that, taken together, will greatly improve our ability to produce and manipulate energy and material. The basis for this manipulation springs from the ability to cluster charge into a dense, tightly bound packet instead of using individual electrons. It is also about what can be easily seen and proven right now with some pointers as to what lies ahead. The original discovery of this charge comprehension and containment process was made in 1980. There was a description of the discovery process and electronic devices using such charge clusters published privately in 1987. Several patents on electronic systems were subsequently issued in both 1991 and 1992. Others have published 3 papers on the structural aspects of charge clusters. In 1996, a paper was published by the authors on a low energy technique for causing nuclear transmutations in matter. All data produced so far is exploratory in nature, and none of it is thought to be the last word. During the year spent working on the electronic aspects of what I called EVs, a Latin acronym for strong electron, there were many sightings of very intense effects that had no place in an electronic technology. These effects were just swept under the rug, so to speak. Since work in the electronic phase was over, I have been busy digging out energetic effects from under the rug, dusting them off, and seeing what they were. The effects have since been quantified to a degree that produces some utility, but there are still many mysteries left uncovered. This paper is largely a discussion of some of the minor or ancillary effects found. Sorry. The good stuff that has been found will be published later when there can be no arguments about its utility. Striking effects. In the lingo of charge cluster technology, a strike is what an EV does when it hits a target. The effects produced can be very dramatic if the conditions are right. One mystery that had to be resolved early on is the difference between a spark and an EV. It was found that there is none. A spark is simply the visible ionized gas trail left by an EV, although in some sparks the EV is so weak that it is barely detectable in the trash surrounding it. Every spark made has an EV running out in front of it. In addition, the EV has electron feelers running ahead of it to tell it what to do. To demonstrate the above mentioned point, an ordinary spark in air produced by an induction coil can be used to strike a foil of aluminum. What is seen under magnification is a mark that is characteristic of an EV strike. Figure 1 shows the front side of a 6 micrometer thick aluminum foil that has been struck by a spark carrying an EV. Figure 2 is the backside of the same foil. It is clear that a well-organized energy form has penetrated the foil. There is no lateral motion showing, and this is a definite indication that the energy form was short and was not a long string of current with a tendency to meander over the surface. Metals are hard for an EV to cope with, as the electron supply from the metal is too great for the EV order to continue. As a result, the range of penetration is only several micrometers in a good conductor. Dielectrics and semiconductors is another matter entirely, and a penetration range of over a millimeter per kilovolt. Am I on the right?
Yep, yep,
Should I be
yep.
asking?
No, you're right over.
Okay. Kilovolt is common. One convenient configuration for penetrating a dielectric with an EV is to lap the edges of two dielectric plates that are about a half millimeter thick and press the lapped edges together. This gives a nice cross-section view when the EV strike the macro crack producing by joining the edges. The plates are then placed on a grounded foil of aluminum and an induction coil sparked to the crack on the side of the dielectric away from the grounded aluminum. Figure 3 shows an example of this method applied to aluminum oxide having a melting point of 2050 degrees centigrade. As can be seen, there are 7 distinct trails showing in the center of the edge view of the alumina plates. There is a slight taper on the top and bottom of the plate that makes the plates touch in the center and not at either the top or bottom. Such a tapering technique gives control over the entry and exit angles for the EV. This is important as it has been found that an EV must be terminated and its characteristic impedance just like any fluid flow or electromagnetic wave. When the flow encounters a discontinuity, a reflection occurs. In order to have the EV make just one pass through the material, it is necessary to taper the output side as a small horn. If this is not done, sloshing will occur for both the EV and material it propels. Sloshing. Sloshing would seem like a trivial thing to consider if it were not for the fact that it is caused by a sloshing EV, and this implies a very high degree of coupling between the EV and surrounding material. Figure 4 shows the entry side of one of the traces carved by an EV as shown in Figure 3. This particular channel was not well terminated, and the EV rebounded several cycles before exiting the system. By carefully examining the overlap pattern of the material at the top of the channel, it can be seen that waves of material are laid down in a successive and diminishing pattern. More decisive evidence of this effect is shown in Figure 5 and Figure 6. Figure 5 is a color optical micrograph of an EV strike on lead oxide glass. It can be seen that the material has been laid down in a sequence of two strokes. If the photograph is reproduced in black and white, it is not as vivid as in color. Figure 6 is a SEM photo of the same strike and gives a different view of the effect. As can be seen, the borehole is quite smooth and two waves of deposit are apparent, and proper EV impedance termination is almost accomplished. Figure 7 shows an example of a strike on lead glass that is even nearer to termination. In addition, this micrograph shows a dual EV strike in which paired EVs travel. Okay. In addition, this micrograph shows a dual EV strike in which paired EVs travel side by side and enter the material at precisely the same time. The freezing pattern testifies to the time coincidence. A third strike also shows in Figure 7, but is not related to the dual EV. The technical importance of the sloshing being an indication of EV movement is that as a measurement method, we are able to see EV movements in places not heretofore visible. Some of the motions are essentially frozen in place. As will be shown later in a later section, the cause for an entirely intense microscopic light source can now be seen as an oscillatory EV motion. Material disruption. A question that comes up with the sloshing argument is concerned with how an EV manages to get around all of the material that is in its way. The answer to the question is it doesn't. The EV goes through the solid or liquid material. When measured separately, an EV appears to be a collection of electrons that has a number density equal to the number of nucleons in a solid. It thus has an electron population equal to Avogadro's number. Under such conditions, if an EV passed through solid material, there would be one extra electron contributed to the lattice per nucleon. Correspondingly, the electronic bonding of the material would be nullified and a liquid or gaseous phase would result. After passage of the EV, things would take a few moments to sort themselves out and return to the lowest energy state available. This would be classed as an atomic disruption process and not a conventional melting. Presumably, the energy required for disruption is less than for melting, as the electrons are not necessarily excited. Evidence supporting this assumption is shown in Figure 8. This is a micrograph of the material that was deposited on a 6 micrometer thick aluminum foil placed near the exit side of the boreholes and the aluminum oxide. There are two overlapping deposits showing, indicated by a slightly circular configuration, that have an almost electrified appearance. Figure 9 is a magnified view of one circle material, and it shows high degree of consolidation for the deposited liquid. There is also the characteristic dimple showing that is similar to the entry side view of an aluminum target as shown in Figure 1. Aluminum oxide has a melting point of 2050 degrees centigrade, and yet It has not raised the temperature of the thin substrate material in any perceptible way. Even a thin coating of low temperature wax on the surface to serve as a temperature indicator remains undisturbed unless the aluminum oxide directly contacts it. Additionally, the surface tension of the aluminum oxide fluid is so low that it runs out to almost an atomically thin edge, and there is no indication of evaporation of the aluminum oxide onto immediately adjacent surfaces. This behavior is contrary to what happens when a molten particle of aluminum oxide from a thermal melt strikes the surface. Under this condition, even a particle of a few microns in diameter partly melts into the aluminum foil, has a high contact angle, and also evaporates a decoration of aluminum oxide on the immediately surrounding surface. The conclusion that can be reached from these observations on disruption is that this is not a very high temperature process, and that it does not take much energy to do the job. Another conclusion concerning the order of events can be found by referring to figure 10. This is the backside of the 6 micrometer thick aluminum foil immediately under one of the deposits. What can be seen here is a strike mark similar to figure 2, which is characteristic of the exit side of an EV strike. It appears that the EV has transited the aluminum oxide and struck the aluminum foil before the aluminum oxide fluid arrived. This is in line with an earlier conclusion that the EV first disrupts the material by passing through the solid, then liquefies it and imparts momentum to the fluid. In this scenario, the EV is what moves the fluid. Guide the EV and you guide the fluid.
Susie, can I just interrupt a little bit? Is he saying that a spark for a spark gap? He's saying that's an EVO. That's EVOs or something. The electric spark.
Yeah, yeah. He's basically saying at the very beginning.
I mean, in a way, it's like looking at nature from a different angle to the other physics models, isn't it? It's like looking at anyway, but
Everything begins and ends in the light. It's kind of like the thing. You ever see the Mandelbrot set? I'll talk about that afterwards. But if you look at these images, I mean, it's kind of invokes a lot of that stuff. I mean, if you, how far down these holes go, it's really getting at the infinite patterns and geometries. It's really neat.
he's redefining physics to a certain extent and electricity.
I think one of the most important things he said is one mystery that had to be resolved early on is the difference between a spark and an EV. It was found there is none. The spark is simply the visible ionized gas trail left by the EV. So that's kind of what you're talking about, Brendan. Thanks, Lacey. Let's keep going.
Okay, I'm gonna read the subtitle for the figure 11. Figure 11, time exposure of a side view of a 0.001 inch thick aluminum foil coated with silicon carbide being sparked by an induction coil from a moving electrode located on top of the photo. The small jets seen coming from under the foil have penetrated through it. Playing with sparks. The following experiments graphically shed much light on EV energetics and point to a very interesting new light source and deposition method of refractory materials. All that is needed is an aluminum foil coated on one side with silicon carbide grains and an induction spark coil. Figure 11 is a side view of the aluminum foil described above that has a time exposure taken of it as the spark coil is run across the foil sparking on the silicon carbide coated side. The spark containing the EV strike the silicon carbide grains bores through the coating and gains enough energy to penetrate the aluminum foil and emerge into the air on the other side. In the photo, the sparks start at an electrode near the top of the frame. Streaks are seen running down to the silicon carbide side of the foil that is held edgewise to the camera. In many places, jets of light appear past the foil. There are two types of jets showing. One of these is short and blue, while the other type has a white-orange appearance. Several things can be seen on the front side of the foil. At the ends of the foil, both on the left and right side where there is no silicon carbide coating, the strikes do not penetrate at all. In the active center region, the flares coming from the silicon carbide coating are large and are moving backward toward the spark electrode. Reflected material due to sloshing from mismatching the EV causes this spray. The EV penetrates many of the sites but is pulled backwards and carries the material with it. A typical borehole entry is shown in Figure 12 for a silicon carbide coating that has been mixed with epoxy to hold it on the aluminum foil. Figure 13 shows the exit hole in the aluminum foil used to support the silicon carbide and act as a ground for the spark. The borehole is fairly clean for a process that is capable of fluidizing a material with a melting point of 2,600 degrees centigrade and projecting it to an unholy velocity. In fact, when a special test is set up to determine the thermal gradient at the edge of the borehole, one comes to an astounding conclusion. Either a gradient of over 26,000 degrees centigrade per micrometer exists here, or this is a non-thermal process. To arrive at this number for the thermal gradient, I used a very low melting point material for the silicon carbide binder and let the EV pass through the composite target. In one example, paraffin wax was used for the binder, and both colloidal graphite and silicon carbide were used as fuel in two separate tests. The boreholes produced by EV passage were so perfect that the cusp of the intersection between dual EVs could be seen. This indicates that the entire 2,600 degree temperature drop occurred less than 0.1 micrometer of space. That is an astoundingly high gradient for essentially bulk material. Therefore, it must be something else. Deposition process. If material from the exit of a borehole is collected on a substrate, such as aluminum foil, it will be found to be deeply implanted in the substrate. Typically, a silicon carbide slug digs in about 20 micrometers. Of course, in the example just cited using an aluminum foil carrier plate, the aluminum plate will also be deposited. An example of a single shot of silicon carbide of aluminum shows in Figure 14. The high velocity of the deposit not only buries it deeply, but also scatters it with high energy. Even with this scatter, there's not much material lost, and for some mysterious reason, very little shows up in the region of the aluminum exit hole immediately above the deposit. It all seems to be blown sideways. The appearance of the deposit can be varied over a wide range by velocity control. Figure 11 shows a scattered deposit of silicon carbide, and Figure 8 and Figure 9 represent coalesced deposits. And adapting this process to a useful technique for producing mechanically robust materials with high efficiency, it is necessary to properly overlap many successive shots. To do this, either a slurry source of material or multiple layers of source material are needed. Microthrusters. If the source of material propelled by EV action is viewed sideways, a small shock cone can be seen coming out of a micro nozzle. The spacing of these cones is typically 7 micrometers at atmospheric pressure. That represents a very high velocity and high specific impulse. The electrical energy input to push a 20 micrometer diameter by a 100 micrometer long slug of material to this velocity is only 20 microjoules. When a measurement of the ejected particle velocity is made in vacuum using a source that is vacuum compatible, The highest particle velocities found or velocity found is 1 centimeter in 50 nanoseconds. These particles are detected as ions. There is also a large number of slower ions and neutral particles made at the same time. The propulsion mechanism is not known in detail, but it could be similar to those used in xenon clusters excited by laser irradiation, and that similar containment mechanism could be used for both. The xenon cluster technique produces particles with megavolt and energy levels. A fantastic light source. Instead of catching silicon carbide on an aluminum foil, as was shown in figure 14, we put a photographic film in the place of the aluminum. A situation is set up for seeing the photon image of what happens coming out of a borehole. Additional data can be collected if we put a fine meshed metal screen over part of the film to act as an object for point projection microscopy. The screen also acts as a filter of radiation, allowing us to detect any X-rays present. If incandescent particles come out of the borehole, we also have a reorder for their motion across the surface of the film. By doing this simple experiment, we can collect a large amount of data with little effort. As a matter of fact, all of the data in this paper was collected by an expenditure of less than $300 for all the apparatus and material. Of course, it took a lot of time and the data could not be communicated without the microscopy used. Nevertheless, the exploration was carried out with only the most meager apparatus. This is not difficult work, and it seems that a lot of this kind of new energy science can be carried out in garages. When the experiment is set up as indicated, the photographic result shows in figure 15. This is a positive image showing white where light strikes the film. Several things can be seen. On the top and upper left, there are white spots with streaks emanating from them. The central white spot is where the borehole of ejection was located. This corresponds to the long plumes shown on the lower side of figure 11. The silicon carbide hit the gelatin surface of the film and rolled across it, leaving trails that eventually stopped, and in some cases turned back and parked as spherical balls. This is another piece of evidence that the ejected material was not hot enough to harm emulsion, although it produced visible light. Note that some of the white spots do not show any deposited material. This is a fact that was confirmed by careful examination of the emulsion surface. These spots correspond to the short blue plumes on the lower side of figure 11. What happened here is that the EV first emerged and then turned around due to mismatched conditions and took the load of fluidized silicon carbide back with it to make a large whitish plume showing on the top side of figure 11. In this case, all of the momentum that had been given to the fluid was taken back by the EV and then restored in the opposite direction. This is normally thought to be a difficult job. At the risk of being even more conjectural, I would suggest that someone look at the new rules for mass manipulation in this EV domain. And this says figure 15, positive image on photographic film of silicon carbide ejection from borehole. Point projection images from 200 mesh screen show an outlined area. Figure 16, magnification of region number 1 from figure 15. Figure 17, point projection magnification of screen image taken from another shot similar to figure 15. There is a grid that faintly shows within region 2 of figure 15. Figure 18 shows this magnified. This is the edge of a 200 mesh copper grid having a 0.001 inch wide wire spaced every 0.005 inches. The grid is used for projection microscopy. Region 1 is outlined and magnified in figure 16 and is one of the projected images caused by several point light sources produced by the process. Close inspection shows grid images at various magnifications caused by the light source occurring at different distances from the screen. The closest spacing from the screen produces the largest image. Figure 17 is a similar image from a different shot that has slightly higher contrast and a better grouping of the light sources. The grid distortion is caused by the different magnifications being melded or merged together due to different locations of the light source. And another image magnified from figure 15, figure 18 was taken from the top section of the screen called region 2. An image of the screen corner can be seen in this photo. Figure 18, magnified view of region number 2 in figure 15. The lower portion shows an image of the 200 mesh screen used. Many depth specs can cast a sharp shadow from the point light generated by EV acceleration. One of the interesting effects shown in figure 18 is the ball of silicon carbide that has come to a stop near the lower right corner of the photo. It stopped near a small conical shape on the surface. There is no thermal damage to the photo emulsion showing here in spite of the high melting point of silicon carbide. Immediately above the cone is a particle of dirt that casts two shadows in almost orthogonal directions. These shadows are caused by the two light sources shown coming from off the screen. There are also many other shadows sharply cast from even smaller specks of dust. Each of these particles attests to the size of the light source that illuminated them. The sharpness of the wire image essentially gives an upper limit of the light source length, and the sharpness of the shadow from dust specks give the lateral dimension upper limit. Taking these two bits of data together, it can be said that the light source has an upper limit in size of 5 micrometers for both dimensions. This is about 1/4 the dimension of the board channel. From other measurements, we know what the velocity of an EV is under normal conditions. They typically run at about 0.1 the velocity of light in a vacuum guide, but slow down according to their interaction with the medium they operate in. Under the operating conditions used here, a turnaround time of several picoseconds is expected. This is an estimate from other measurements and not a direct measurement of existing conditions. This turnaround represents an acceleration of charge that usually produces light emission. It is essentially synchrotron radiation that would produce a wideband chirping spectrum. The length of the light pulse would thus be on the order of several picoseconds. It is the turnaround time or stopping rate that exercises a major control over the emission wavelengths. And the geometry used here, where the dimensions are somewhat large and the retarding field is soft, one would expect nothing higher than optical frequencies to be generated, and that is what is found by using filters between the light source and the film. The highest frequency lie in the UV region. It has been found from past experience that stopping an EV on a low inductance, high mass material can generate X-rays. The stopping rate is high under such conditions. In other experiments using double EV structures, where shock waves were set in collision, gamma emissions were measured. This is a common occurrence that could happen under many experimental conditions accidentally set up and could be the cause behind reports by others on gamma emissions. The intensity of light source during its brief life can be estimated from knowing the sensitivity of the film and the distance from the source. These estimates indicate that around 100 billion photons were emitted. This is an extremely intense source for a short period of time. Low energy nuclear transmutation. Data taken from a previous paper presented a low-energy nuclear reaction conference shows evidence of an EV transmutation of material. Data from this paper are shown in Figure 19 and Figure 20. Figure 19 shows an EV strike on a foil of palladium that had been previously loaded with deuterium. When this foil is analyzed in detail with an X-ray energy dispersive analyzer, it shows as clean palladium in all places except those bombarded with EVs. Figure 19, EV strike on deuterium, loaded palladium foil.
Deuterium, deuterium, and
Deuterium.
palladium.
Okay, thank you.
I think it's like heavy water. Isn't it right, Eddie? It's heavy. It's a form of water, H2O. It's something like H3O or something. I can't remember. I think it's heavy water, deuterium, or
hydrogen isotope.
Well, sorry.
I think that's right.
Yeah, it's
So it's hydrogen. It's a hydrogen isotope, isn't it?
Everything passes through hydrogen. When you collapse hydrogen, there's a ton of energy. But yeah, I mean that's. But anyway,
it's heavy hydrogen. It's an isotope of hydrogen, isn't it? Yeah, that's right.
Yeah. Okay. Cool. Thanks, Lacey. Let's keep going.
Figure 20, X-ray analysis of the crack shown in Figure 19, showing new material produced. Many of the bombarded areas, but not all, show that nuclear conversions have taken place. The new materials showing are mostly silicon, calcium, and magnesium. Figure 20 is an analysis of the EV damage area shown in Figure 19. These converted areas typically show a brittle characteristic before bombardment. It is known from extensive bombardment of pure materials that efficient nuclear conversion cannot be expected from simple, large EV structures. Conversely, when an EV is loaded with nuclei, nuclear conversion does occur, but it is not nearly as efficient as the process using a loaded substrate. The explanation lies in the need to have very small EV structures for quick stopping. In a loaded material, it is likely that fractal emission of electrons occurs arising from the brittle nature of the material. This produces small EVs. Observation of EVs with diameters down to 0.1 micrometers is easily done. Below that value, analysis is complicated by the granularity of the substrate material. It is the size range of around 200 angstroms that is of interest for transmutation. However, large EVs serve as effective triggers for partly loaded areas capable of producing fractal emission. Free energy. Now we come into the main topic of this conference, and at this point, our bias will be shown. Theories and ideas have almost no value at all in our world. Laboratory demonstrations are worth very slightly more. These notions stem from trying to sell paper inventions and finding it is a process that stops creative work. To my way of thinking, it is only a properly engineered device that has real value, and that is what we are trying to do. Throughout much of the work on EV energetics, it has been obvious that we get more energy out of certain experiments than we put in. The work being described here also falls in that category, although the engineered version using any of these effects in an energy-producing device falls short of a great thing. The really good stuff for legitimate products is still to come, and we are working on it. Trying to market a bad free energy or cheap approach is not good for the field, even if it sounds wonderful at first. Getting a good lab result from an idea and being able to work it into something better is our forte. Making a theory out of good ideas or results is not for us. However, I have to have some vaporous thoughts to hang on to as I go along my path. To do this, I have learned that standard words must not be attached to new notions. One invariably bends the work to follow the standard direction instead of taking the new path that is the proper one. An example of this is that, as far as I am concerned, cold fusion results may not be nuclear at all when the base cause is found. We see that EV processes are capable of causing similar low energy nuclear reactions as a side effect. I do not know what the base cause for these is, but I am inclined to say a few things bearing on potential energy producing techniques that I use as my own tenuous guide rail. Take the example of a steam engine that could run without putting any energy into producing steam. As long as everything else worked the same, that would be pretty good free energy device. We have talked about being able to bring about a phase change, changing solids to gas by using an EV disruptor. Looks like a steam engine is in here somewhere. Go to a well-known process for producing really high temperatures, such as molecular dissociation and recombination, and use the same type of process to dissociate nitrogen and hydrogen. Can such a cycle really become an engineering reality? Even though these processes could possibly be made to work, one is still left wondering where the energy comes from. In a search for an answer to this question, I have made sure not to hang a conventional name on the process. Having done this, I have complicated the communication of ideas, but that is not a problem as long as we don't talk to anyone until the final machine we have completed communicates the notions for us. In an effort to get across in this paper the notions that guide me, I'm going to fracture conventional words in such a way that some meaning is implied as long as they are not taken too rigorously. I'm going to use the notion that the energy excess we see comes from a form of electron annihilation. Of course, I don't mean the usual electron positron type. Instead, I am going to invoke the latest buzzword and say that it is fractional electron charge I am talking about. If electron fraction or fractions really exist, as some experiments by others indicate they do, then I will use the process of their annihilation into electrons for my energy gain. One of the main requirements is to take electrons apart in an energetically favorable way. The existing experimental process is said to require a high magnetic field producing a vertical flow of charge. That is likely to exist in an EV. And another look at the problem from a wider viewpoint, there are several things about an EV that are different enough from the conventional theories to lead one to wonder if electrons are contained in their usual form. From many EV measurements, it has been found that there is a diminution of expressed of expressed charge in an EV. Thank you. It is easy to account for the number of electrons that go into them and come out. The dimensions are also well known, but classical calculations of surface field are several orders of magnitude below what one would expect. Additionally, EVs have the measured charge to mass ratio of an electron, but with the low expressed charge problem, they seem to have lost mass also. There are still a lot of basic things to work out because at this point, we don't even know if we are dealing with contained electrons or something else. There is one thing found in common with all energetic processes involving EVs. The EV must be irradiated before energy is released in any form. That is possibly why the EV strikes shown in figure 11 that land on the bare aluminum do not show any energy release. On the other hand, those that have to irritate their way through the silicon carbide give up much more energy as they regenerate. This observation could just be an illusion caused by a bad power match to the spark. I treat the irritation process as one capable of disheveling an electron into fragments as only one phase of electron existence so that these fragments can later unite and release energy. That's also fusion. Two things are certain. One, EVs are always involved in any of my processes capable of interesting energy permutations. And two, lots of new rules are needed to cover new findings. From my viewpoint, I see only a good future for this energy field. Acknowledgement. The authors are everlastingly grateful to Tom Shanks for his total support of this work.
Okay, well done.
Yeah, cool. Thank you, Lacey. That was excellent. One of the things that stood out to me, they're talking about it is the size of around 200 angstrom that is of interest for transmutation. So there seems like there's a certain size that he's looking at to do that with.
What page is that on?
That is on page 12, and it's the second paragraph, right at the end of the second paragraph, just before free energy. You can see size of around, yeah, 200 angstrom. So I think that's pretty important there. Based on a spark-like propulsion process giving significant velocity produce shock cones. That's really interesting to me as well, too, actually. Yeah. An excellent paper. Does anybody have comments or?
Yeah, Lacey, can you go to the very first figures? I think that's the page 2 or 3. I wanted to take a look at those again. Yeah, those two dimples. Blow those up. I guess I'm puzzled at all the musings in this paper. Clearly, Ken Shoulders is trying to come to some conclusion as to why the ingress and egress responses look so different. So the first pair of pictures there, figure 1 and 2, why, for instance, isn't there an outward explosion material? It's dimpled back in on itself. He's talking about fusion characteristics and sloshing and everything else. Typically, an impact. Yeah, and typically an impact, which is in figure 1, is normal like a bullet hole, and the exit wound would be splattered everywhere. So he tries to address this in multiple ways in a very qualitative way. And it is the secret, I think, of this soliton-like, or actually pure soliton wave transmission that's occurring with this.
You can see in figure 6, he's talking about the sloshing and how it sloshes back and forth and it creates that like a rim kind of. So in figure 7, he's got, and it's kind of interesting. I don't know exactly what he's talking about when he says impedance matching, but in electronics, to get perfect wave transfer, you usually have to have the impedance matching perfectly. And I think when he does that, I'm not sure exactly how he does it, but that's how he gets these holes that aren't sloshing, essentially. The other thing here is
what's he using to image them? Some kind of a microscope or something?
Yeah, a scanning electron microscope. He talks about it in there. Yeah, SEM.
Which he designed himself. Did he design the microscope himself?
Yeah, maybe.
Because he designed a lot of his instruments. He built a lot of his instruments.
He did, actually. So he probably did design that himself, as a matter of fact. Yeah, he was brilliant. I mean,
the Wrights machine, he built his own optics. You read about that? You ever see the story like John Bedini and trying to rebuild the Wright machine? Because he could like see virus in action, but he built it all himself. The guy was just pure genius. And he actually cured cancer too with frequencies. And of course, they wrote him off.
Lacey, can you go down a couple of pages? I just wanted to review all these exit wounds, if you will. I would argue the secret in understanding what he's talking about here is precisely what he's focused on. Why do the exits look so different from what you would expect? It's not purely inertia and impedance. There are nuclear effects. He's relating to sloshing, which is a very qualitative effect. That's a massive arm waving. And he's putting this entire body of data out there for this convention without really solving it. And I like that. He doesn't know, but I would argue that the secret in understanding EVs is exactly what he's talking about here, and he doesn't understand it. He does not understand why those exit wounds look so clean, why the sloshing is backflowing in a nuclear fusion process or something, why that soliton falls apart on the backside of the aluminum foil, and then the thing ejects itself back into the material. Why is that happening? That all has to do with unique quantum charge characteristics and various other things. They also would look just like a bullet wound, with the backside of that exit wound looking like shit, scattered everywhere, and it does not. That's the secret to understanding these, and that's why he's going over this. But he doesn't have any solutions. He's just waving his arms in a qualitative way, thank God, and asking other people to take a look at this. I'm going to study this paper in detail. I'm going to download it and look at it in detail.
One thing he says, I'm concerned cold fusion results may not be nuclear at all. When the base cause is found, we see EV processes that are capable of causing similar low energy nuclear reactions as a side effect. I think that's pretty important.
Yes, he's conflated a number of very interesting things that occur at the nuclear level. Even partial charge electron fractioning, as he's talking about.
Yeah, and I think that, like I was saying before, it is the size range of around 200 angstroms that is of interest for transmutation. One of the things that I think is going on is as it goes through the material, these transmutations are occurring, because we saw in the very first one that we did on the Proton 21 laboratory that was in Russia, and they shot through a copper slug, an EV. On the other side, there was all kinds of new materials being transmutations with different types of materials on the backside, right?
Yes.
So
he talks about some calcium magnesium effects in here, but I don't think unless I missed it, he's not talking about any transmutation, nuclear transmutation of elements in these pictures. He's not pointing to any calcium or magnesium being created from an aluminum EV interaction. And so, did it not occur? If there's no transmutation here, then this is a huge curveball, because I would expect it to occur in every EV strike. Especially
Alexi, can you blow those pictures up a bit? Can you blow those pictures up a bit?
I think
thanks.
I think he just wasn't it wasn't the focus of this paper, and that's necessarily because it is, we've got it in other papers that transmutation does occur through.
Yes,
it's actually common. I mean, transmutations happen all the time. Like, we even like to believe it's this impossible thing that only happens in stars. It's like stars are being born, like literally thoughts, bright flashes, and this is what's going on at all times in all space, all around you. It's just.
And also, Paul Laviolette was talking about parthenogenesis, when atoms spawn other atoms, or electrons spawn, or protons spawn other electrons. I was thinking, I was talking to just the other day about Wilhelm Reich. He was saying he was taking Justin said he was taking Freud's idea of, because Sigmund Freud, the famous psychologist from the first part of the 20th century, he thought everything, I mean, he was an atheist guy, but he thought that everything, that the meaning of life was sex. He thought sex. So I was thinking, I mean, in one extent he's right in a way, but he's not right in another way. But so Paul was talking about the cells in your body are reproducing all the time. The atoms, the protons produce a spawn. Paul's talking about protons spawning other protons, atoms spawning other atoms, stars. Anyway. But I think Justin was saying Wilhelm Reich was taking Freud's idea and extending it into alternative physics. things like that, to do with chi energy and things like this.
Yeah,
Anyway.
it's amazing. They
But
locked him
he-
up in a prison at one point, even though like all he was doing was healing sick people. I'm pretty sure that prison is in Pennsylvania. I'm not.
And that was my
Like
sister
right
was
up the
making a
road.
comment about going to church when she was going to visiting the local church.
They did that
She
to a
came
lot
back
of
and
the
says to
like
me,
people.
"Of Christianity, no sex,
Do
no
you,
sex,
do you
Christianity."
guys want to maybe stop the recording and we can carry on with our conversations here?
yeah, so I want to go back to figure 13 here.
Okay.
And
So
do you,
that white ejecta is not transmuted materials according to this paper. He's not bringing it up.
mhm.
It's
Do you want
silicon
me to stop
carbide.
recording right now or like stop recording after we talk about figure 13?
Well, yeah, we can keep recording for a little bit,
Yeah.
but let's just stay on topic.
Yeah,
I
so
don't think there was any talk about this. This is just a proof of like what effect this has. You know, when you have these basically unspoken effects at these really high voltage, high temperatures. I mean, literally, it tears holes in reality itself, the fabric of
but it's not
reality.
quantitative. He's waving his arms at this. What is that white material in the ejecta on the back side of that hole? It's very clean. It's not splattered. But is that silicon carbide? He's talking about wax and silicon carbide, very high temperatures. But he does not go to say anything about transmutation. I would expect that if they sampled that white material around the opening in figure 13, there may be some calcium and magnesium and some transmuted material here. But why is it so clean?
Even the common materials that we're led to believe in, your little periodic table, that's not even close to like. So again, I go back to this Randy Mills character, and if you watch his latest video when he's talking about where the technology stands, just watch that guy talk. It's amazing. He'll show you solid xenon. It's a wait a minute. How do you do it? When you actually understand the real nature of the atom and how that collapsing centripetal and centrifugal vortex and how they combine and things like that, it's actually like, and even he says it like, kind of like as an aside, like transmutation and changing materials is actually quite easy, and actually there's a lot of custom
Yeah.
materials like
Well,
exotic.
I'm not questioning that, Michael. Not at all. I'm questioning is why he did not mention it in this paper. He's in front of a convention giving this paper. Why didn't he talk about it? Can we go through some of the others real quick, Lacey? Just scroll down under 13 and I want to kind of look at them all again real quickly.
You want me to go to page 8?
Yeah, just keep going down page by page. And that one splattered all over how single shot silicon carbide ejected from a borehole into a foil of aluminum.
This is the same stuff Bob Grenier's doing. Like he's showing these boreholes and whatnot, and all over the place. He's been measuring all kinds of transmuted elements. I mean, like I think Bob did more, but it looks exactly the same.
Yes, but he's talking in very general physical terms here: sloshing, boomeranging back into the hole, nuclear fusion, all these things. And I would offer that the actual mechanism in blowing a hole in the aluminum foil is a combination of several things. And he is very open to that idea. I like the paper because he's very open with his qualitative descriptions. He does not come down on one side of the fence in one way or the other. He's just literally throwing it out to this convention. Figure 14 shows the scattered deposits of silicon carbide, and figure 8 and 9 represent coalesced deposits. It's silicon carbide, which is coated on the aluminum. It doesn't say anything about transmutation. In adapting this process to useful techniques for producing mechanically robust materials with high efficiency, it is necessary to properly overlap many successive shots. Jesus. Keep going down.
Wait, isn't that exactly what he's saying? No, he's saying silicon carbide is coming out of an aluminum foil.
Yeah, but why not calcium and magnesium? You know the transmutation has to occur with this kind of an EV charge density. It is changing quark spin and everything else at a nuclear level, at a subatomic level. Why didn't he discuss this? Keep going. Yeah, no, these are very interesting. I saw this. This is from the aluminum foil at figure 11. Keep going. I just kind of want to review all these. Yeah, this is a curveball. It's just dust. Keep going. That's interesting. There we go. This is LENR, low energy nuclear transmutation, kind of a cold fusion. All right, so he refused the transmutation here in the first paragraph. And he's talking about deuterium, the heavy water. It's not tritium, it's deuterium. X-ray analysis, the crack is showing new material produced. Yes.
He is saying mostly silicone, calcium, and magnesium. It's just that he's not focusing on transmutation in this paper, basically.
When this foil is analyzed in detail with an X-ray energy dispersive analyzer, shows that clean palladium in all places except those bombarded with EVs. The transmutation, very good. All right, take that back. He is referring you to it a little bit here. Keep going. Keep going, Lacey. Keep going.
That's the end, I think.
That's the end.
That's the end. All right. All right, good.
Yeah, cool. All right, well, maybe let's stop the recording now and we can talk more about it.